Okay, welcome back. Chapter 17, Part 2. All right, so if we put those two thermodynamic functions together, enthalpy and entropy, we can get a measurement called Gibbs free energy. It's actually what they call the Gibbs-Helmholtz free energy, but there is a difference between Gibbs version and Helmholtz, and at this level they only emphasize the Gibbs version of it, where it represents the useful energy available for work. Okay, so what does that mean? That means that we're going to take a look at conditions. We're going to take a look at what the two thermodynamic factors are, and then we're going to add in the thermal environment. And from there, we can get a measurement as to how much energy we can either get from the reaction. And this plays a big part in Chapter 18, where we're running electrochemical cells, in other words, batteries, and trying to figure out how much power, how much energy we can get from the battery. Or it's how much energy we need to put into the reaction to get it to occur. So really what it's talking about is spontaneity. Does this happen with you putting in energy, or does this happen as a result of, regardless of whether you put energy? It's not a measurement of whether a reaction is impossible. What it's saying is, let's look at the conditions we have. The reaction can occur, but do you have to put in the energy? Or you can look at it this way, in terms of equilibria, it will give you an indication of whether the forward reaction occurs spontaneously, or whether the reverse reaction occurs spontaneously, or whether we're dealing with a system that is already at equilibria. So again, it's not an issue of impossibility. People seem to get that confused in my experience with students. All of these reactions are possible. It's just a matter of coming up with the conditions under which it's spontaneous or non-spontaneous. Now, from a scientific point of view, that can be a mixed blessing. Things that are spontaneous are good because you don't have to pay for the energy, the fossil fuels, for instance, or the battery or whatever to provide the energy. But in the same sense, things that are spontaneous are not controllable. So there's a safety issue, there is a yield issue, how much yield you get from it, how much of your reactants are consumed. Where non-spontaneous, like most pharmaceutical reactions, tend to be non-spontaneous, because even though you're paying to put in the energy to run the reaction, the nice thing is you can control it. As soon as you remove the energy, the reaction stops. All right, so if we get a negative value for delta G naught, and delta G naught is just standard conditions, but it doesn't include temperature. Delta G is highly temperature dependent. If it's negative, that means the reaction is spontaneous. If it's positive, that means the reverse reaction is spontaneous. Now, in terms of graphing this stuff, it's just like delta H. To get to our transition state, we actually have a delta G of activation, where we're dealing with this difference in energy here for delta G between here and here. And then we have our overall real delta G that we're concerned about, which just compares reactants to products. But there are two different things there. We can take a look at delta G for activation energy as well. And again, that has to do with how much energy do we need to put in to get to that transition state. But just like with delta H, the only thing that we're doing for delta G is comparing the products and the reactants. We don't care about the pathway in which we get there. So for delta G, there's two types of reactions. There are things that are exergonic. Those reactions are spontaneous under those conditions, like in the first example. And there are reactions that are endogonic, where we are creating higher energy products, and therefore we're going to have to pump some energy into it, so the reaction is not spontaneous under those conditions. But here's the thing. We use the term exergonic and endergonic, and not exothermic and endothermic, because they're not necessarily related. With delta G, there's a temperature component that's not included with delta H. So with delta H, we say exothermic. We said that exothermic reactions may be spontaneous and they may not be. Exergonic reactions are always spontaneous, because under these conditions of temperature, we're producing a certain amount of useful energy. So the difference in the diagram here is with delta H, you're looking at the internal energy of the reactants and products and comparing them. Here, you're looking at the entire environment. What is the environmental condition for energy of the reactants compared to the environmental condition for the products? So therefore say, well, if you look at this and you're looking at it without being careful, and say, all right, well, the first one is exothermic. Well, not necessarily, because again, it's not measuring internal energy here, it's measuring the entire environment. All right, so we said delta G naught is a state function. We're only comparing the condition. So we're going to say that the state is the condition and the environmental condition of the reactants to the environmental condition of the products, and we don't care about how we get there. But the difference between that and delta H naught is that delta H and delta S are are not really affected much by changes in temperature, whereas delta G is highly affected by temperature. So again, delta G considers the entire environment, including the thermal energy. So we have three components here, and this is called the Gibbs-Helmholtz Equation. I'm sorry, Helmholtz. I always say Helmholtz. It's Helmholtz. And we have to take into account the delta H conditions, delta S, but also the temperature. Now, temperature is in Kelvin, so there are no negative values for temperature. We said with delta H, you can have either exothermic or endothermic, so we could have positive or negative values there. And with entropy, we're either increasing the entropy, maybe we're dissolving a crystal, or we're decreasing the entropy, maybe it's the formation of a precipitate. But delta S can also have positive or negative values, but temperature is always going to be positive. So the difference between Gibbs free energy and the Helmholtz free energy, we're only going to deal with Gibbs, and the reason why we're dealing with Gibbs is because of two issues. One, if you're dealing with Helmholtz, you got to deal with a closed system. And in our laboratory work, when we get back to the lab, we wouldn't have a closed system. We'd have an open system. And for Gibbs, you're talking about constant pressure condition. That just means if we're running it in a lab, we're running it under atmospheric conditions, where with Helmholtz, you're talking about keeping the volume constant. So it's a little bit of different aspect in terms of work energy being pressure and volume change. Here we're dealing with, all right, we're going to let the pressure be constant because we're going to run it in our lab. But with the other one, we can't allow any expansion or contraction. So that's a very specified view of the free energy conditions. So we only focus on Gibbs. It's more practical. All right, so if we have delta G naught and it's less than 0, the reaction is spontaneous under standard conditions. Again, notice they don't mention temperature here. They only mention 1 molar concentration and 1 atmosphere of pressure. Now, if it was regular delta G, then delta G negative would also be spontaneous, but it would be spontaneous under that specified condition, not under standard conditions. So delta G naught greater than 0, then we're looking at a non-spontaneous. Now, here's the thing. If delta G is negative, they're talking about the forward reaction. The forward reaction is spontaneous, so that means the reverse reaction is non-spontaneous. And for delta G greater than 0, then the forward reaction is non-spontaneous, but the reverse is spontaneous. And if delta G naught's equal to 0, that doesn't mean the reaction is not occurring. It just means that we have reached a condition of equilibrium between the forward and reverse reaction. They love to ask these questions, generalized questions about Gibbs free energy, dealing with certain delta H and delta S conditions, and dealing with the temperature changes. Sometimes we said delta G naught is highly temperature dependent. So in this first example, we're dealing with delta G greater than 0, which means that we're dealing with an endothermic reaction. So we're dealing with some sort of positive value for delta H. And for delta S negative, that means we are decreasing the entropy. So think of it this way. You have two driving dynamic forces there. Enthalpy, positive. Okay, nature tends towards stability, so things tend towards exothermic. However, this is endothermic. And then we said that nature tends towards disorder, which means positive delta S, but here we have negative. So we're kind of violating both major thermodynamic principles here. Not violating, but we're going against the natural trends. And that can happen, but it's always going to be non-spontaneous. There is no temperature at which we can get some sort of spontaneity. So when you have both of these factors going against you, yeah, you can make the reaction happen, but you're going to have to provide energy. It's never going to be spontaneous. And for the opposite, where we have an exothermic reaction and we have an increase in entropy, it's following both of those thermodynamic guidelines. So regardless of the temperature, you're always going to get some sort of negative value for delta G, which means it's always going to be spontaneous. And then they like to ask, well, what if we mix it up? What if we go against the enthalpy, but we follow the entropy? And what if we follow the enthalpy rule, but we go against the entropy? All right, let's take a look at it then in terms of the mathematics and then in terms of guiding principles. All right, so from the mathematics, delta G equals delta H minus T delta S, the Gibbs equation. And if delta H is exothermic, then we would have a negative value. If the temperature is always some sort of positive value because it's in Kelvin, and delta S is an increase in entropy. So in this first example, we're following both of these principles. So no matter what we put in for numbers here, we're always going to get a negative value. So this term right here is going to become positive times positive, which is positive, and then we wind up doing negative minus a positive, which always comes out to be negative. So always spontaneous. In the example where we are violating both principles, not violating, I got to stop saying that, going against the general trends, delta G is always going to be a positive value. We have positive for an endothermic reaction, and then we have a decrease in entropy. So again, we're going against both thermodynamic guidelines. So we wind up with a positive for our first term, and then the second term winds up being negative, so negative times a negative. So this always comes out to be positive. Positive plus positive gives you positive, so it's non-spontaneous under all conditions. Now, what about if we follow one and we violate the other? Okay, again, that word violation. I mean, go against the trend of the other. So in terms of exothermic, this is going to be spontaneous under low temperature. I would focus on the enthalpy part, because in terms of this mixture where we're following one principle in this first example with negative delta H, and in the next example with a positive delta S, I'm going to focus on the enthalpy values, because the enthalpy values numerically are a lot more important than the delta S values. So, well, what temperature conditions favor endothermic? Higher temperature. So in the last example where we're dealing with an endothermic reaction, high temperature favors that endothermic reaction, whereas in the example where we have exothermic, lower temperatures favor that reaction. All right, so here's a chart summarizing it. Again, if you are following both guidelines in the first example, negative delta H, positive delta S, you're always spontaneous. You don't have to worry about temperature. If you're going against both trends, then it doesn't matter what temperature you use. It'll always be non-spontaneous. Again, that doesn't mean that, by the way, that I'm talking about the last example here. That doesn't mean that the reaction is not possible. It just means it's not ever going to be spontaneous. You're going to have to add energy. Again, if we have one thing following a guideline, like in the second example where delta S is positive, or in the third example where delta H is negative, then we have to consider the temperature. And I said focus on the delta H. An increase in temperature favors the endothermic. So at high temperatures, positive positive is going to be spontaneous, and at low temperatures, negative negative is going to be spontaneous. Okay, this is annoying. Calculation of delta G naught from delta S and delta H. Remember when we did delta H and you had to do the summation of the products minus summation of the reactants? That's what you're doing here, except for you get to do it twice. Yay! Delta S and delta H. And then put it together into the Gibbs equation in order to get delta G. So here's our reaction of smelting iron again. Whoever smelt the iron dealt the iron. Ho 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 ho. I say out into the void of nothingness. What is delta G naught at 25 degrees C? What is delta G naught at 500 degrees C? Well, I'm going to do this. First of all, I got my book with my little thermodynamic values, so you're going to need that. So I'm going to write them out for you. Hey. Okay, so here we go. So we look up these values, and you might as well pause at this point and copy those values down for each of the reactants and each of the products. Again, note that delta H for hydrogen and iron are 0 because they're elements, but they do have a entroscopic value. All right, so once you return, we can move on. So we need delta G is delta H minus T delta S. Really? Good thing I prepared in advance. Is this it? Yeah, here we go. Sorry, this is so tedious. I don't want to work this out while I'm on the video because I keep messing that up. And it's not as easy to change as it is when I'm face-to-face with you. All right, so first I'm going to do the delta H, and delta H is going to be my products minus reactants. The nice thing is I don't have to include hydrogen and iron, so the only product I'm dealing with is the 3 moles of water and the 1 mole of iron oxide. So I get a value of positive 100 kilojoules per mole reaction, so that's endothermic. So we would expect the spontaneity to go up as we increase the temperature, which is what you see in the answers. The first answer is positive 56.6 kilojoules, but then at 500 degrees it becomes spontaneous, negative 10.6 kilojoules per mole reaction, and that would make sense if this is an endothermic reaction. It favors the endothermic. So for delta S, I'm doing the same thing, except I now also have to include values for the element iron and for the element hydrogen. Make sure I multiply by the molar values. And we get 138 joules, and then we have to remember that delta H is in kilojoules, so I had to convert this to kilojoules. I didn't actually show the calculation. Let me just divide it by 1,000. So if delta H is positive 100 kilojoules, delta S is positive 0.138. We can put that into Gibbs-Helmholtz. Helmholtz. And for the Gibbs, we said that it was 25 degrees C, so that's 298 K. And I get 58.9 kilojoules per mole. Now, why are the values different? Because the thermodynamic charts have changed over the years, and 20 years ago the answer was 56.6, but with the update of the charts it's 58.9. Same thing with delta G at 500. Now that we know the delta H and the delta S values, we can just change the temperature. So at 500 plus 273, that's 773 Kelvin, and it still is spontaneous under those conditions, except for now it's negative 6.67 kilojoules per mole. And again, as you're going through those calculations, feel free to pause and take your notes and do whatever you want with it as in terms of going through it. I'm just going to go through it quickly to save time in these videos. In fact, we are probably at the end of this video now. So I'm going to go ahead and stop here.